Hello, everyone. Welcome to week 3, year 1 of PhD Live. Got a really special episode planned today where I actually start working on some of my research project. Um, the the main topic I'm going to talk about today is a method called Markov Chain Monte Carlo. But before I get into that, let's see, what other updates do I have. Um, week 3 of PhD Live also corresponds to week 3 of my classes starting, which have definitely been picking up in pace. Been covering a lot of material in Python programming, which I have some experience in, but getting a lot more of it rapidly now. And also sort of just general good practice programming techniques like version control, working through GitHub, and also working through like various IDEs, development environments. Um, Lots of statistics, lots of particle theory, mostly review, but trying to get back up to speed on quantum field theory, which I haven't done too much of since last year. And the exciting thing about this first mini project I'm working on is that it looks to kind of bring all of those things together and give me a chance to apply them towards something useful, and hopefully even publishable. So this to introduce what this method is, first I want to talk about Monte Carlo methods. I'm going to give like a I don't know, hopefully like 5 minute or 10 minute review here of what I've learned about these topics so far, and then I'm going to get into some actual coding work, which I have to do by tomorrow. So I'm just gonna work on that. Um, a Monte Carlo method is a pretty widely used technique, specifically in particle physics, as far as I know, but I believe in quite a few other scientific fields. Basically, in any situation where some kind of result is dependent on a probability distribution. Maybe that probability distribution isn't kind of explicitly known. Maybe you don't have an exact formula for it, but you have some approximations of its shape. Maybe you do have an explicit formula, but it's not one that can be integrated, like summed over in an efficient way. Maybe it's a very high-dimensional probability distribution, dependent on all sorts of variables, and so trying to work with it analytically just becomes too complicated too quickly. So Monte Carlo methods are a numerical way of getting around these problems by sampling over a distribution randomly, just choosing points within whatever the range of possible parameters is, and then depending on the method, assuming that you're able to at least evaluate the distribution. Maybe you don't have an efficient way of summing over or calculating a function of this distribution, but you can at least, given some values of the parameters, you can say how probable those values are. If you can do that, then you can choose random points and sort of simulate the distribution, and as you go, try to calculate whatever function, whatever other observables you're interested in, and get a result that, as you do more and more sampling, eventually approximates the real result. So this is the kind of the method I'm going to be working with, is a more specific way of doing this, because specifically, I guess it's fair to say, specifically in Bayesian statistics, which I was talking about a couple weeks ago. You're looking to rather than given some sort of parameter, some sort of theory, calculating the probability that you get a certain data set out of it and trying to sort of predict the results of an experiment. You're going the other direction. You have the results of an experiment, and you're trying to find the probability that your theory is correct. So in order to do that, you're taking a set of data that you've been given from some experiment, and you have some prior estimate on the distributions of the parameters that sort of represent your theory. So you have a rough version of your theory, and you want to use this data to make it a little more exact, a little more accurate. Um, the way that this method comes in is by the way, the reason I'm glancing to the left is because I have this massive book now on numerical recipes, which was kindly gifted to me, well, I assume temporarily, by my supervisor, and it has a nice little chapter on this. So I'm just checking myself that the goal is to calculate a probability distribution on the parameters of the theory that represents sort of the new, more exact theory, taking into account the data. Monte Carlo method provides a way to do this because we have this distribution, and we're going to try to sample it using the information that we have from the data. But the I guess the other thing I should mention first is that even in this simulation approach, you were talking about a very computationally intense task. So it's when you're doing this sampling, it's desirable to sort of minimize how much additional data you're storing while you're doing the sampling. So in sort of a standard Monte Carlo method where you're just, they probably have some good pictures in here. Yeah, this is a good example. We're using random sampling to find the value of pi by just uniformly sampling points in a square. You have the outline of part of a circle here. It's very easy to check for any given point whether it's inside the circle or out of the circle. And as you sample these points, just by calculating the ratio of how many points fall in the circle versus not, you approximate the value of pi. In this sort of random sampling, this is very efficient because each of these points is totally statistically independent. None of them are at all based on the others, and that works fine. When this doesn't work fine is in situations where you're working with either a very high dimensional probability distribution or a very sharp probability distribution, because this means that, looking at the sharp example first, if you imagine there's a peak sort of right in the middle of this distribution here, and everywhere else is quite flat probability-wise, close to zero, then the wide majority of the points you sample are not actually going to be useful to you because most of them are going to need to be rejected and thrown away in order to ultimately match this distribution. So you're wasting a lot of resources. There's geometric reasons why in a higher dimensional space, and this is a two-dimensional simulation, it's not so visible in 3 dimensions, but in higher dimensional spaces, like much higher, talking in the tens or hundreds of dimensions, which is reasonable when the dimensions are not like spatial dimensions. We're just talking about possible parameters of a theory. It's called a phase space sometimes. What happens in those higher dimensions is that the volume of some kind of polyhedron, some kind of like dimensional shape, the wide majority of that volume is concentrated towards the edges of the shape. You can sort of think about this in 3 dimensions, how like in a 2-dimensional square, let's say you sort of envision the square that's like an inch in from the boundaries. You just trace out like a smaller square in the middle here. What proportion of the area would that be? I don't know. It looks like it'd be roughly half or maybe a little less. But if you do that with a 3-dimensional cube, if you do the same thing, the ratio of volume that's left in the middle is a lot less. And that goes to the extreme in higher dimensions. So even though you think you're sampling, well, you are sampling something uniformly according to the volume, but if there's interesting features of the probability distribution within the middle of that region, you're going to be missing them, or at least wasting a lot of resources trying to get those. So the way that we get around this is by using something called a Markov chain, which, generally speaking, is any kind of statistical model where you're generating random states one after the other. in the simulation from before, each of these states is generated in the same way according to some algorithm, probably just picking a random number from 0 to 1 and another random number from 0 to 1 and plotting that coordinate point. So each of them are identical. A Markov chain is different because it allows the probability distribution of each point to depend on the last point. Only the last point, though, not any of the others that came before that. So in a way, all the points are still identical in that they're only depending on one other point. So there's no preference between very early points in the chain and very late points. But they are correlated with each other. I think the term is that they're autocorrelated because anywhere in the chain, you have a very high probability of things repeating themselves and staying close to each other, and ultimately settling into some sort of stable state. So a simple example, they might not give it in here. Yeah, okay. Yeah, this is kind of the standard example of Markov chains is a birth and death process, or sometimes like a predator-prey process, where you have one population that has a certain rate of eating another population, and then that population has a certain rate of eating the first population. You could sort of model this with a sort of repetitive function that takes in the populations at any given time, and according to how many there are, eventually it'll settle with either some sort of stable state where they both stay at the same number, or one of them will dominate over the other. Like there's only a few ways that it can go. And Markov chain Monte Carlo methods take advantage of this by defining this chain to be a series of points within the distribution. And it turns out that it's possible to set it up in a very specific way so that the distribution of all these points that you get over time, so it's sort of just like you can picture a random walk going around within some space, that with time and enough points, the distribution of the locations of those points will match the probability distribution that you're trying to simulate. And it's incredible that this is something that you can do because it's very efficient, but the math works out. And I'm not going to go through all that math ahead of time, but I'll sort of talk about it as I go into the code here. The specific implementation that I'm working with is called the Metropolis-Hastings algorithm. And this way of doing Markov chain Monte Carlo depends on a sort of secondary probability distribution called a proposal distribution. So this random walk that's going through your sample space, there's kind of the fundamental question of, okay, I have a point in this one location. How do I choose my next point? You could just a naive approach would be to just say, okay, kind of forget about where that point was, just choose something anywhere else in the distribution, and kind of forget about this previous step in the chain. That wouldn't really be a Markov chain. That's going back to the random approach, and you start to run into these issues of sampling in lots of places where the distribution is low and you're wasting time. So the philosophy is that if you're in somewhere in the distribution that has a pretty high probability, hopefully somewhere near you is also pretty likely to have a high probability. So rather than moving somewhere far away, you try to move somewhere pretty close to you according to some distribution. So maybe it's a Gaussian, just centered on where you are right now. And what the algorithm does is it takes the point it's currently at, moves to this candidate point, and this is where it uses the information available to it with the actual probability distribution. So it calculates its probability at its current point and its probability at the new point, and it finds the ratio between them, and then it multiplies that by the ratio the other way with this proposal distribution, so that points that are further away basically become more biased to not happen. Like a further away point will only get selected if the underlying distribution is so high there that there's a really good motivation to go there. And yeah, Markov chains are cool. Thanks, Logan. And but the important feature is that this is still even despite that approach, this is still not a deterministic algorithm, which is important for reasons I don't quite understand. But with a simulation like this, you want to retain a kind of stochasticity where every time you run the algorithm, you're going to get a slightly different result, but on the average, they're going to approach this distribution that you want to get. So the way that that's done is that this ratio that I'm talking about between your current probability and the candidate probability, you end up with some kind of ratio, and then you run one more random number generator and use that ratio as the probability of whether you accept that point and go there or not, or choose another one. So even if that point gets a really low score, it's not all that good in terms of the underlying distribution. It's also a little further away in the proposal distribution. There's still some chance it'll get selected. So this, for example, avoids situations where maybe your algorithm is in a pretty good area of the underlying distribution, like some kind of mound that does have pretty high values, but it can be a local maximum. There could be a much bigger mound over here, and because it just can't get over this hump, it's not able to find the other one. But there's this randomness involved that says that eventually, if there is a better feature of the distribution over here, it will eventually get there, no matter how unlikely it is in any single iteration. I think that about sums up the math. That was about 10 minutes, right? Hopefully. So I have some code in Mathematica, which my supervisor has kindly shared with me with sort of a sample implementation of this. So this simple example is the distribution. It's only in 2 dimensions, and we have a circle. So yeah, square root of x squared plus y squared, circle of radius 0.5, and it has some sort of error on the radius. So it's a ring that is sort of drifting off gradually towards the center and also towards the outside. And this is the test one that I'm working with. So a successful simulation looks something like this. You have this cloud of points that are generated by the chain as it goes around. And the more points you run, the more uniform this becomes. And this hasn't been run with a crazy amount of points. I think this was only run with, like 10,000? I think just like 10,000 samples. Yeah, it looks like about 10,000, maybe. So it's not perfect. It should be an exactly symmetric distribution, and there's some areas that are getting more points than others. But the longer you run it, the more exact it becomes. And often in practice, and it's not happening today, but hopefully within a couple weeks I'll be doing this rather than with this sort of test donut. I'll be doing it on real neutrino data, trying to estimate some parameters to do with neutrino mass. So what's a parameter that we'd be trying to estimate here? Probably the radius. So we have a distribution, and in this example we're defining it. We're saying what the radius is. But maybe in real life this radius is something we'd like to measure, and we have a lot of data points, and we're using those data points to generate this distribution of what the radius seems likely to be. And this is a plot of the radius. So even if the sampling isn't perfect, there's areas that are getting oversampled or undersampled. Even with this lower number of samples, you start to get a pretty clear picture of what the radius is. You could do some sort of statistical analysis on this and get a confidence interval about what is the mean radius. What is the 90%? What do we believe within 90% is the radius, and you get some sort of error bounds, which is in the end like the publishable result. So I'm going to switch over to my exciting new camera format here, where how do I do this? Yeah, this is what I do. Yeah, now I'm smaller. So I've started writing. This should be showing my C code, right? Yeah. Okay. Using my new favorite IDE for C code, which is Code Blocks. Give me free stuff, Code Blocks. I've set up a semi-replica of this mathematical implementation in C, but I'm trying to do it a much more object-oriented way. I'm not very familiar with Mathematica. It seems very function-heavy, where you come up with a lot of different functions and have them calling each other, and that's just it's one approach to programming. I definitely prefer an object-oriented approach, where what I've done is defined two classes, but the main one, I've defined a Markov chain class. For those of you who are not familiar with object-oriented programming, this is a style where, or a method where you create kind of a cookie cutter. You create this template of a structure that's going to be, you're going to be storing data in, you're going to be doing some kind of simulation in, and you're going to make more than one of whatever this thing is. So the cookie cutter is the way that you, every time you want to make a new one, you run this thing and you get a new identical copy, and you can do stuff with it. You can save data in it. You can run whatever the functions are that are associated with it. It'll have certain methods that it's able to do. Trying to think of a good analogy. Like I think in video games, a good example would be a car in a racing game. It would be silly to program every car in a racing game from scratch, because most of them move probably in very similar ways. They have similar graphics structures, similar controls. You want to have a car class, and every time a new car needs to appear on screen and be drivable and stuff, you create a new object of that class, and you can do stuff with it. You can whatever commands it has available, you can use. And sometimes you make some more specific changes, but you're working with the same general structure. So my Markov chain class has the way I've set it up is sort of dividing it into the input variables, which are the things that probably do get changed every time. The number of steps that you want to run the Markov chain for. There is a quantity called burn-in steps, where before the Markov, you sort of run the Markov chain, but don't save the data. So it accounts for the case where maybe you start somewhere, you don't actually know what this distribution looks like before you run the Markov chain. You start somewhere which turns out to not be a very good area of the distribution. So you want to let it run for a while and get to the good area, and then start taking data. Because, ultimately your distribution will still be the same no matter what, but you're kind of pointlessly putting in some data that you know is bad at the beginning, and you don't need to, because ultimately the distribution is going to get to this stable state. I think it's called the ergodic property or something. So no matter when you start, as long as you run it long enough, you get the same result. What else have I got? Internal variables, so stuff for saving the state of the chain at any given time, which will just be a vector of floating point numbers. A little later, a way of calculating observables, so whatever function it is that we'd like to extract from this distribution after we simulate it, that'll be there too. In this case, that'll probably just be the radius. This part got tricky, and I'm not 100% sure I did it right yet, but passing. I need to be able to save. I need to be able to store a function for the probability distribution that we're trying to simulate, the prior distribution that comes in before the new data, and also whatever the method is for getting a new state. So in this case, the Metropolis-Hastings algorithm, like that specific way of getting to the next state from the current state. But that's just one algorithm. There's a lot of others in my big red book that I might want to try at some point or kind of optimize on my own. So I need to be able to pass functions as inputs to this class, and I'm hoping that I've set that up correctly here. Yeah, just some stuff for printing out the data into kind of a spreadsheet afterwards. I think that's all the data storage of this class. And I've started writing the functions for inputting all that those parameters for how the algorithm should run, inputting the functions that have to do with the distribution that's being simulated. Then the Metropolis-Hastings algorithm itself, that's going to require the most work to write. I've done a little of it. And then post-processing, which will include saving this stuff to file, providing some kind of user feedback while it's running. And then after the fact, I can't decide if this should be in the same class or not, but ultimately afterwards I'll need to be able to plot the data. I think it will make more sense for that to not be in the same class, because I'll want to be able to save just the data, and you don't need the Markov chain anymore. You just save the collection of points you got, and then I'll want to plot that later. So I'll probably define some other class that's like Markov chain data to just save the data and display it in various graphical formats. And then I have this MC parameter class, which I made this separate as a way of letting the user input specifically what was that? Oh, this is just the way that the user sets the bounds over which they want to simulate this distribution. Though I'm kind of forgetting why I got it separately now. Anyway, yeah, that's where I'm at. This is just the header file. I think it's good practice to put the class definitions in the header and then put the actual function declarations in the main C file. But if anyone wants to criticize me on that, I would welcome that. I really need to get in the practice of leaving like a little bookmark where I was last working, because I totally forget now. I guess I think I wrote this first Metropolis-Hastings algorithm, so I'm gonna look through what I did here again. This should just be what happens in one step of the algorithm. So based on the current state and of the Markov chain and whatever the parameters are, so the parameters being the boundaries. Is that right? Oh, I see. Okay, yeah. This is comes back to that proposal function. So the um, the way that we choose the next state of the Markov chain from the current state. This is looks like this is providing two different ways of doing it, and I can probably come up with some better ones than that. Saying, okay, here's my current value, and it's somewhere in this range that it's allowed to be in. You could just randomly choose something from that range, and that's what they're doing in this flat distribution, which is actually that's not that's independent of where the state currently is. So the only Markov chain effects are going to come from the underlying probability distribution. Not sure if there's advantage to that. And this normal one creates a Gaussian around wherever you currently are, and it looks like takes whatever the range between like the maximum and minimum allowed values. So like in this graphical example, it would just be the size of the box. Wherever point you're at now, it's making a Gaussian with standard deviation 1/40th of the total size of the box, and using that to generate points. So that's where this draw new state function, which I haven't actually defined yet, but it'll be initially one of these two, and it could be any method for drawing the next point. So candidate is the current is the current state of the Markov chain. Candidate is potentially the new state. So I do this draw new state, then I calculate the underlying distribution and the prior distribution at that spot, and then this is, I mean, this one right here is kind of the main Metropolis-Hastings condition, whether to take that point or not. So I take that. This is just running a random number generator, which I think I defined. Yeah, up here I'm just using the one of the C random number generator libraries. So it'll take a uniform distribution between 0 and 1, and if it's less than that probability, it'll accept it. It'll make that new. It'll make this proposed candidate the new current one, and it ups the count. It keeps a ratio of how many points are getting accepted versus rejected, and I guess as that stabilizes, that gives you some clue of the distribution itself stabilizing. And I think that's kind of all that has to happen here. Because then what will happen next is in between these states, it'll update the distribution, I think. Just rearranging my camera. There, now you can see a little more of my code and a little less of me. So I guess at this point I would calculate if I had some kind of observable I was trying to calculate, I could calculate it here. But I don't. So I'm just going to leave that for now. And this is where I actually run it over and over again. Oh, cool. Running it actually crashed my C, so that's fun. Wow, why did that go so badly? Okay. Min was not declared in this scope. Oh, okay. That's probably something with how I declared a draw new state. Draw new state. Oh, yeah, I'm silly. This should return a standard vector of a double. Not just a double. That'll do it. That'll fix it. Maybe. Oh, I need to fix it here too. Data types are fun. Here too. Min was not declared in the scope. That's concerning. Let's look up. Oh, I have to include something. Include algorithm. Alright. I can include that. Oh, I did include that. Maybe this will do it. Maybe not. Right. Oh, okay. So yeah, semicolons get me every time. Oh, it's because it's oh, that's why. Yeah, I probably didn't actually need to do this. There we go. Okay. So the lesson is learned that C is not smart enough to compare an integer with a floating point number. And I haven't actually defined this yet. So that seems to be working now. So Markov chain, this I can unfortunately just kind of copy. Yeah, so we're going to just run this. Run one iteration of Markov chain. Oh, this should be a for loop. Let's look up how to do for loops in C, because I don't remember. I'll take that. Yeah, that makes sense. Yeah, Mathematica for loops or do loops are just very strange looking to me. And then I want to run this progress report. function, which I haven't written yet, but that's that. Yay, cool. Syntax works. And this is pretty much the same thing, except what is the difference? Oh, the difference is I'm actually, saving and storing the results. This is the one thing I do like about this Mathematica technique is the reap and sow statement, which I have never seen anything like this, but it's a way of like running a for loop and natively collecting together all the results into a single array in this very nice little structure. And I think I'm gonna just have to do that manually here, but it's nice. Like, yeah, I can't deny that is a very nice way of doing that. So just running it for n steps this time. Still want the progress report. Still want the number of steps. Oh, I see now. Okay, that's interesting. It wasn't clear to me what this did before. The save interval. Yeah, this was not clarified. Interval of steps to save. Okay, I probably should have read into that better. So when this is running, as an example down here, it's doing 1,000,000 steps, I think. Wait, test example, and then 1,000,000. Where is MC defined? End steps and burn in steps. Save interval. Okay, and this is running with 1,000,000 steps. So it starts by doing 10,000 burn in steps, and then it runs 1,000,000 times, but it only saves every 100 times. Okay, I'll take that on trust for now. That's my only option. Okay, so my results file is, I have it as a vector of doubles, but that's not what I want. No, I want it to be a vector of doubles, because it's going to store all the points as they go. That's what's going to happen. Yeah, okay. I wonder, yeah, that's probably fine. Okay, so you have a vector, and you want to add some new vector into it, and you just do this pushback thing. Okay. But I want to add a whole vector into it. Okay, I think I know how to do that. Wow, this is disgusting. I didn't know you could use a not equal symbol directly in code. That's really bad. I don't like that at all. All right, I guess the way to do this is resolve pushback. And I want to put a whole vector in there, so I should define that vector of doubles as save state, and that's going to equal. Can I define vectors this way? either push stuff into it, but this is what I'm wondering. Can I just do that? Vector, ooh. Yeah, I'm gonna just do this the way I know how to do it. That's safe. Yeah, so what am I gonna put in there? I'm gonna put current state, which is, ooh, this is interesting. How do I want to store, do I want to store the whole current state in there, or do I want to go element wise? I think I want to put the whole current state in there for now. I can change this later. Yep, and then I put the whole new saved state into the result. Is it results or result? It is result. That seems pretty reasonable. Progress report. That should probably happen last. Okay, that's kind of how that goes. Does that scan? No. Oh, it doesn't want me putting... Probably a vector is not the best way to do this, but I'm doing it anyway. Ooh, can I do this? This would be kind of cheating, but... Haha, yeah, that's nice. Okay. That's a really weird way to do this, but okay, that's fine. Then... Saving to file. Yeah, that seems important. Okay. Back to that file, C++. There's always a lot of Googling involved in my coding. I don't know if other people do it this way or not. Oh, wait, Malcolm has advice. You need to push into vector. Oh, yeah, I can't read the comments. Push into vectors IIRC. What does that mean? What does IIRC mean, Malcolm? Resizable list. Oh, I see what you mean. No, I'm trying to. What I'm trying to do is because every state of the chain is a vector, and I want to save that vector and then also the probability of the chain. So just a vector plus one kind of. I want to make a vector of those vectors, and that'll be kind of the full data output. Oh, if I remember correctly, that's an interesting abbreviation. I'm gonna use that. Yeah, you're right though. Yeah, I think pushing is the only good way to do it, except for this. The copying is fine because this current state, I define that as a vector here. So they're the same data type. This is fine because this is only a temporary data structure anyway. I'm going to put it all in this file just as like column format and then pull it out later before I want to plot it. I think that's the best way to do this. this is not a good way to do this. Open the file. Yeah, I'm probably not going to do my data set exactly the same way anyway. I'll just do this part myself. Oh, that's interesting. He sorts the whole Markov chain by how... Oh, by how strong the probability distribution is. I wonder what the advantage of that is. Yeah, I can do that. There's got to be some C library for exporting. Yeah, that's what I'm looking for. Okay. Okay. And then let's see. First, I want to output the headers, the data labels. I think that's what I have. Oh, this is interesting. I guess you can iterate over standard vectors. Yeah, because I did that, but I need to add one for fit. Yeah, because I'm gonna list all the output parameters and then the probability, the posterior probability, like how probable it is in the distribution. I think that's what that means. So Seems wise. Yeah, I like the sound of that. Yeah, that seems about right. And then, yeah, so that's just putting the data headers at the top of the file, and then I want to do the same thing, but with the results. I'm going to go through the whole result, and let's call this J. Yeah, and for every row in the results, I want to go through that row. So we're going to just have this again. Oh, this is going to get messy. Alright. Yeah, I'm just going to go through the row of results J. Ooh. Oh, or do I want to do it this way? That's probably right. Really am freewheeling here. That looks kind of right. Yeah, for everything in there, I want to print that also into the file. I should probably do like a new, assume there's like a new line thing that I have to do in between here, right? I think I should be ending lines in between. Yeah, that seems about right. I mean, until I actually test this, it's kind of meaningless, but I think that's close enough to write. Assuming it actually runs. And it doesn't. That's fun. Yeah. iOS has not been declared. Oh, yeah, that's wrong. That's probably also wrong. probably something I need to be importing here. What is it? Something like that. Might just be that. Alright, that makes sense at least. Oh, it's mad at me for something there. It's probably this, it's probably this thing I did. Oh, that worked, really. I wasn't expecting that to work. Cool. That should be making the whole data file now. Oh, I was going to do the data precision. That's right. Yeah, I still want to do that. That's important. Yeah. Yeah, because this way I can sort of say what the precision is going to be. File data precision equals 8. I'm not going to use the sorting thing yet. No, wait, not there, not there. I probably need to import something again. Once I have everything imported, then I won't have to import anything ever again. IO manip. Coolsies. Yeah. That looks good to me. And now, what happens in the progress report? That's where I say something like, I guess I just want to have an ongoing output file. Oh yeah, and then I need to close the file when I'm done. That's important. At least C++ makes writing, like, yeah, just messages to the terminal pretty easy. I think I kind of literally just do steps. Yeah, something like that is good for now. Just say what step I'm on. Oh, and maybe like a out of. Steps. That seems pretty reasonable. I should declare it std as a namespace, but I haven't yet. Multiple definitions of E2. What's that mean? Oh. Did I accidentally define that twice? I think I did. Yeah, this seems like a header file issue. Maybe these shouldn't be here. Maybe these should be here. That worked. Cool. Okay, we're in business. Great. I think I can actually. Do I want to stop for the night? So what still needs to be done is actually define these distributions that I want to input, and essentially set up my first test case. So input the parameters, input the the underlying distribution, so the square root of x squared plus y squared thing. That shouldn't take too long to type up. And then kind of just hope that it runs. And then I do want some ways of plotting these things and pulling that back out. Yeah, reading the data back in and plotting it. Yeah, I think I'm going to call it there for tonight. This was good progress. Cool. Thanks to everybody who tuned in. As soon as this is running, I'll probably do another stream on pretty short order, maybe over the weekend to actually, or early next week, but definitely the next stream will be showing this running and then sort of talking about how I'm going to extend it to the actual data, which will go back to some of the papers that I briefly talked about last week, looking at some of those again. So yeah, tune in soon. PhD Live signing off.